All right, so hello everybody. I'm Rem. I've been working at Forder for the past 4.5 years. I've been with the product since probably day one, so I'm very familiar with them. Like working here. I'm going to talk about Kotlin Coroutines today. Mainly, I'm going to use Apache Storm as just a use case, as something practical to make theoretical examples more understandable in day-to-day terms. So I'm going to skim briefly about what is Storm. I'm going to skim briefly about what we do at Forder. And basically, then we're going to move to looking at coroutines and how are they useful. So generally, what we're going to talk about is some introductions, and then we're going to do a walkthrough of basically us trying to implement a generic Storm vault using coroutines. And the journey we went through from a product which is not so good at the beginning to something that is much better, more suited for the job. And we're going to look at the step-by-step transition. And I chose that method of showing the issue because I believe that it's much better than just showing a perfect example, a good specimen, and explaining the different parts. Rather, I'm showing you transitioning from a mindset, from an old mindset to a new mindset, and I think that's a much better platform for learning. So a bit about Forder. We're providing trust-related decisions to our merchants. Basically, our clients are e-commerce, some of the biggest that are out there, and we are providing them with our knowledge about trust. So finally, at the end of this chain, of this funnel, basically, we decide on whether money should change hands, on whether a transaction should be approved or not. But before that, we interfere in a lot of points during the process. We determine whether or not a client should be able to change their password, whether or not they should be prompted with multi-factor authentication, and all sorts of those things. Basically, we pride ourselves on making the playing field safer for our merchants to reduce friction and sell more. Currently, we have globally 170 employees. Our decisioning systems have very low latency. In the median, it's 200 milliseconds. The more complex decisions, the transactions usually, the stuff that involves real money, they can go up to 700 milliseconds. That's in the 99th. But what we're going to talk about today is this last bullet. It's our high throughput event processing system. So basically, as you understand, we have a lot of people surfing our merchants' websites, and we need to kind of keep track of, kind of profile their behavior. So that system, the system that's mentioned here in the last bullet, it processes in a daily peak of 100,000 events per second. And it's in charge of building the clickstream kind of data corpus that we hold on customers. And when I say clickstream, it's not only clicks, it's much more than that. It's behavioral data. So it's basically events. And that's what we do. It's an important system because it allows us to be more accurate. All right, so this system, the system that I mentioned doing high throughput event processing, is based on Apache Storm. So just an overview of what Apache Storm is. Does anybody here work with Apache Storm? Does anybody here know Apache Storm? Has worked with Apache Storm? All right. So Apache Storm is basically a distributed stream processing framework, which means that it allows us to model a pipeline, a topology it's called. And a topology is made of bolts, which are basically our code, the constructs in which we implement our code. We model this, we connect those bolts using streams into a topology, and then we run our events through that topology. And what stream processing basically means is transforming the stream, enriching the stream, joining the stream, anything that you do on a series of events that you can think of. Bolts are the unit that actually does the computing. Each bolt has an execute method that we as developers need to implement. We're going to look at code examples so that it's going to make it a lot clearer now. Just so we get the basics, bolts can perform I/O, can and do. Bolts are stateful, which means that they are just objects, like instances of classes, and they have fields that they keep. That's their state. And each bolt instance has its own dedicated thread, which if you join that with the previous bullet, that they are stateful, you kind of understand that you don't have to worry about concurrency. You don't have to worry about synchronizing access to your fields when you're implementing a bolt, because only one thread is ever going to execute that code. So no race conditions. And that's Storm. That's just what Storm gives you. A few more things you got to know about Storm before we begin is that Storm has two types of bolts. Basic bolts, which have a synchronous API. They are best for CPU-bound operations like JSON parsing or anything like that. And rich bolts are asynchronous, which makes them optimized for I/O, which means that they can start doing something and they can finish doing that thing somewhere in the future. That's just their API. We're going to look exactly now at how that looks. Just one last thing. As I mentioned before, each bolt has an execute method that we, as developers, need to implement. This execute method, when it blocks, it causes back pressure. Now, back pressure is something very basic to any system that does streaming. It's just the way of coping with slow actors. So in case we have some component in the stream that is currently being slow, we want to cause the whole stream to slow down instead of doing something that would cause out-of-memory exception, because we are too slow and the stream is coming in too fast and all that memory gets bulked somewhere. So back pressure is how we handle slow actors, and in Storm, you cause back pressure by blocking the execute method. So I want to show like two basic examples of bolts in Storm. What we're seeing here is basically a basic bolt, a very simple one too. So we are inheriting off basic bolt class that's supplied by Storm. And when we do that, we got to implement the execute method, as I mentioned. We also have a prepare method, which only runs once. So prepare method is where we as developers can do initializing of the state. And then execute is the way that Storm feeds inputs into our bolt. So this is just a bolt, and we can integrate it somewhere in the topology before some bolts and like upstream from some bolts and downstream from other bolts. And it's going to get some inputs. And whenever an input comes in, the execute method is going to get called. Basic bolts are synchronous. Their API is synchronous. And you can kind of get that from the signature of the execute method. So the execute method, it gets an input tuple, but it also gets an output collector. And this output collector is how we basically emit outputs to the rest of the topology, to downstream topology. And as you can see, this collector is being received as a parameter. So that kind of implies that it's just a single use. It's really tied to that input tuple. And once the method is done, this object basically will get garbage collected. And the next time we get an input, we get another collector. That kind of makes this, this bolt's API synchronous. On the other hand, we have asynchronous APIs, asynchronous bolts, rich bolts, which kind of look like that. So it's very similar still. Now we're implementing iRich bolt instead of iBasic bolt. And as you can see, the execute signature has changed. It's no longer getting a basic output collector. Instead, we get the collector here at the prepare phase. And we need to keep it somewhere, have it handy, and then use it in our async APIs. So what's special about this? As you can see, like maybe you can see it, maybe not, but this bolt and the previous bolt, they're doing exactly the same work. Both of them are getting a key out of Couchbase. Couchbase is a key value store, if you don't know. So basically, Couchbase API is give me take a key and give me back some JSON document. So in the basic bolt, it all was very simple. We had a Couchbase client we called get. We gave it the key, and in the line after, we already had the result, right? Because this line, the get from Couchbase, this was blocking API. So once we called get, we went to ask a question from Couchbase, and while Couchbase was working on the answer, we were waiting. We were blocked here and doing nothing. So that's kind of synchronous, right? That's what synchronous API means. An async API is like inherently, especially in Java, it's inherently more complex. Like whenever we have async APIs in Java, we always have this extra scoping because we gotta supply some callbacks, and just doing the same work exactly, just getting a key out of Couchbase and sending it onward takes a lot more code. And not only that it's more code, it's a lot more complex because we have more threads involved. So I said before that in Storm, each bolt has one thread. Once we utilize any async API, it's kind of implicit that there are gonna be more threads in the story, like the threads that call these callbacks. And these threads, in this case, belong to the Couchbase client. And since we have state here that we need to worry about, this code is a lot more complex than the previous code. If we want to change state, we got to synchronize it. It's hugely more complex now that it's async. But what's good about this code is that this method, this whole call returns immediately. So it never blocks the execute method. So in effect, we send something to be processed, and we are already available to process another input while this is being worked on. And once Couchbase has returned, these callbacks would be called from a different thread, which is optimal, but it's uglier, like a lot uglier and more complicated. So that's Storm bolts in a nutshell. That's a very good question. The question was if I have back pressure. So kinda, you want to answer? No, I don't. There's no back pressure here. No. So as I said, eventually we want to talk about Kotlin Coroutines. And coroutines, what they are is just a flavor of cooperative or preemptive concurrency. So I'm not going to go into the theoreticals of cooperative concurrency, but you kind of all probably know it. If you program JavaScript, you've worked in a cooperative concurrent kind of manner. If you worked with any language that supplies async and await primitives like JavaScript now does, you've worked with cooperative concurrency. Basically, it's just a way for a few execution stacks to share the same thread and just be able to, and it gives the developer the option to suspend his code at a certain point for the code to be resumed at a later time. And it's great for non-blocking I/O. And we're going to see exactly why and how. Kotlin Coroutines, as I said, are just a flavor of cooperative concurrency. And they're very, very similar to Go routines. If you work with Go, the primitives are practically the same, very similar. And it uses the suspend function modifier, which is kind of like what in JavaScript, it's the async function modifier. You declare a function in JavaScript with async to note it as a suspending function. In Kotlin, you got this suspend function modifier. You have no need to call await when you do the calls to that function. So I want to show another example of a very basic coroutine syntax. This is a hello world, and since I didn't mention that, first I want to ask, How many people here programming Kotlin? Like, okay, how many in production? Cool. How many using coroutines? Okay, all right. Okay, so this is basically the coroutine syntax in really a very basic example. So what do we have here? Kotlin is the language written developed by JetBrains. So I'm showing you it in IntelliJ, and obviously IntelliJ has wonderful support for the code. And what you see here, the little squiggly thing, is like how IntelliJ marks the suspending function call. So I have a function here, world. The function is declared as a suspend function, which means that it can only be called from within a coroutine context of some sort. The compiler makes sure of that. And if I delete the suspend keyword, I get a compilation error here saying that I can't call delay from a non-suspending function, because a delay in itself is a suspending function. So in that way, the compiler kind of makes sure. And what does that mean, that this function has to be called from a coroutine context? It means that I have to initialize a context first before I can call it. I can initialize the context with the launch extension method. I won't go into what extension methods are. Basically, it's just a function. So the runtime supplies this function for me to start new coroutines. And I need to, it's kind of different from languages like JavaScript, where you don't have threads, because in Kotlin they needed a way to give you a way to select which threads your code will be running on. So they did it using the scope. It's currently not very important. Usually what it means basically is just which thread pool your code will actually be run on. And global scope means just give me the multi-purpose thread pool. Give me something. Run that. Just run it. And launch is non-blocking. It just creates a new coroutine. It's basically equivalent to starting a new thread object and calling run. It will return immediately. Your thread logic will be happening in parallel. So launch returns immediately, calls world in parallel. World delays for 1 second. That's the parallel of that's the equivalent of sleep with the regular threads. So it will wait for 1 second, print world. The program will immediately print hello. So eventually this program will print hello world. What I do want to say before we move on is I want to focus on this little thing in the end. Run blocking is another way for us to initialize coroutine, but it's different than launch in that it does block until the coroutine finishes. So when we start a coroutine with run blocking, the code inside will execute, and while the coroutine is not finished, the run blocking will block the thread that is calling it. So the main function thread will be blocked as long as this call is running, and which basically makes it equivalent exactly to the thread sleep that's written above it. Is that clear? All right, so the goal, what we like to achieve. Basically, when we started up doing clickstream in Storm, we had low traffic, lower than now, and we didn't have to use rich bolts. We didn't have to use asynchronous APIs, because we could use the basic APIs, keep our code extremely simple and nice, and just add more threads when we need to. We could do concurrency in that manner. Eventually, your traffic grows and grows and grows and grows, and eventually it becomes inefficient, because you're wasting a lot of money on initializing threads that do nothing. Most of the time, they just wait for I/O to return. That's because you were using synchronous API to do I/O. So it's natural. Now, what we wanted to do at that point is just replace all the bolts that do synchronous calls with bolts that do async calls. And we wanted to do that using coroutines. And the reason we wanted to do that using coroutines is that similarity between the APIs. If we could just keep the API that was previously that, if we could turn it into something that looks like that, we can do that with minimal code changes. We can do the entire refactoring, which is extremely non-trivial, with minimal code changes. I'm gonna show an example for that, for what I mean exactly. But the goal in the meantime is just creating a generic Storm bolt that uses coroutines in order to do concurrency. So I want to start with the first implementation that we hatched up. This implementation isn't necessarily the best, as I mentioned before, but it works and it's interesting. So what am I seeing here? So basically now I have a bolt that inherits rich bolt, which means that it has asynchronous API, and in the prepare phase we initialize a coroutine scope. As I said, a scope is just the selection of threads that our coroutine code would actually run on. So right now we initialize a single thread pool. That's crucial for the implementation. If we want to keep our state as one that doesn't need synchronization, we got to keep our bolt single threaded. So we initialize a single thread to run all the coroutines of this bolt. And in the execute method that gets the actual input, we start a coroutine and we kind of imitate what Storm does for basic bolts. And eventually we call the abstract method. So that's what implementers are going to implement. That's where they're going to put their async code. And we just need, and what all the work we do is in order to call that, right? And do the async operation. So as I said, launch returns immediately, and this implementation works, but it's not great. Like, a lot of stuff is missing. Anybody can think of what, for instance, may be wrong with this implementation?
Where's the output?
Oh, so since this is generic, so I'm trusting that whoever implements that will use the basic output collector in the async execute, and the implementers can call that. So, but there is another problem, like you asked before. Where's the back pressure, right? Launch returns immediately. We don't have any back pressure modeled here, and that's a problem, right? So no back pressure, that's a problem. Also, no capacity limiting. So basically, if I have a bolt that does input and output, if this method does, for instance, an Elasticsearch query, and I was transitioning from a basic synchronous API to an asynchronous API, then I'm going from a state where my I/O is extremely throttled, just by the fact that mostly what I'm doing is waiting, to a state where this is a free-for-all, right? Whatever tuples get into the bolt will just get executed in parallel, and theoretically I can start 100,000 requests with my Elasticsearch, DDoSing it and ruining the system altogether. Very not graceful. So, like, okay, so we're using coroutines. We achieved the API we wanted. How would you go about maybe enforcing limits on that, or enforcing or causing there to be blockage here in order to propagate some back pressure upwards? So if you're like me and you are not and I wasn't very familiar with coroutines when I wrote this code, then you will probably go to your Java primitives, like how you would have done things maybe in Java. So I'm going to show you what I thought about when I needed to implement back pressure and capacity limiting, which are kind of tied. They're kind of related concepts here. Okay. So now we have the same bolt as before, still rich bolt. Right now we are initializing an atomic integer in the prepare phase. This atomic integer is the current in-flight. It's gonna be used in order to count how many balls we currently juggle in air, how many requests are currently pending, and we need to do bookkeeping on it. So whenever an input gets into the execute method, we increment the atomic integer. Whenever the coroutine launch finishes, we decrement it, and while we are over capacity, we have this sleep loop here. Not pretty, admittingly, but it works. I mean, it causes back pressure. So while I'm over capacity, I'm going to be stuck in this sleep, blocking the Storm thread, not allowing any more inputs to come in. So back pressure is checked. And also, like the capacity, like in-flight, we're limiting the in-flight capacity just by using the atomic integer. Check. So wonderful. Works good. Also, this worked actually in production.
This code is about
What bug? Why?
if you get to a situation where
This never ends.
where this is like blocking you, and then a lot of new messages coming in.
They can't, because once one message gets stuck here, no other message can come in. This is the only thread calling the execute method, and we're blocking it.
Question: isn't back pressure supposed to provide some feedback to the caller?
So in Storm, it's rigged like that other threads, other bolts call into your thread and try to schedule something. And if you're blocked, if your thread is currently blocked, they're going to get blocked too. So you're percolating the back pressure backwards. You don't really have to like inspect from the outside.
And is there a timeout, or how?
That's a very good question. We're going to talk about timeout right in the next example, but it's a good question. Like every component that does I/O will eventually need a timeout of some sort. So yeah, we're going to look how timeouts are implemented. I want to state something about this code. There is like kind of a bug here, which is non-trivial and is very coroutine related. Like we are very used to having the finally clause of our code. We're kind of sure that it's going to be called at some point. But coroutines, in a way, they're mind-boggling because this call, async execute, what it does is just hide away in the background some async API. So in the background here, we're going to have some Apache HTTP client, for instance, an async HTTP client. And finally, we're going to get into a suspending call in this async execute. Inside, we're going to schedule something with the HTTP client. And we're going to expect that the client will call back on us. And like the coroutine mechanism, the language takes care of that. But the coroutine mechanism, once it's getting called back from the async HTTP client, it's going to resume the execution of our method. But what if the async HTTP client has a bug and it's not calling our callback for some inputs? So in that case, we're going to launch the coroutine. We're going to get into that call, the async execute call, but no code after that will ever be called. That execution stack will just disappear into the ether because there's a bug somewhere in here, like in the async client that is suspending, and then we're never going to decrement the current in-flight. And although this bug might be rare, if the topology is up for months, then we're eventually going to choke up the thread. We're going to choke the capacity integer and basically DDoS the topology. So it's a subtle bug, but it does happen. So like a way to handle that would be timeout. And that also would be killing two birds because timeouts are needed for I/O anyway. So backpressure and capacity limit, is that it? No, we need timeouts. So as I mentioned, we have this bug, which kind of requires us to do something, right? So let's see how we do that using coroutines. All right. So here we still have kind of the same code as before. We still have the sleep loop as before, but now we have the with timeout call. So with timeout is basically, let me just change that to a number. Let's do like that. So what this code means, so with timeout is a coroutine primitive. You can only use with timeouts from within coroutine code. And what it does is basically it lets you define a scope. And whatever is running in this scope is going to be time capped, in this case to 1 second. So if we exceed 1 second, an exception will be thrown inside async execute. And that basically ensures that all this code will be time capped. Personally, I think that's one of the nicest syntaxes for timeout scheduling. All other APIs in Java that allow you to schedule timeouts are a lot less intuitive than this. Just defining a scope, telling the environment that this scope must execute in 1 second, and forgetting about that. And an exception will be thrown in the scope once the time is done. So in that case, that's the way we prevent the bug from before. So now we ensure that whatever happens, even if there's a bug and the async client in the background does not call back on us, we're gonna throw an exception, and we will decrement the atomic integer finally. All right. So as I mentioned before, all this solution is kind of very Java-like. Like this sleep loop, besides being inelegant, it might even be hazardous because like it sleeps for an arbitrary 50 milliseconds. If this execution is like 1 millisecond, takes 1 millisecond, our bolt is basically going to spend most of its time here doing nothing instead of processing things, and that's one. Two, we got this atomic integer, which is weird, and we got a bookkeep on it, and it causes us bugs, and it's not elegant either. So what do? How do we solve that with Kotlin, like more Kotlin natural primitives? So there's a way, but I want to divert your attention first, before I show you like our production solution, to the usage of launch. As I said, launch is like the equivalent of starting a new thread and calling run on it. Would you do that? Would you, in a function that, say, execute might be called thousands of times per second, would you ever dream of creating a thread and starting it in a function that runs tens of thousands of times a second? No. A lot of nods. No. So it's kind of obvious to anyone who programmed anything that threads are expensive and you want to initialize them once, probably in a pool, and then you're going to use concurrency primitives in order to pass inputs into your threads. Now, what we learned from working with coroutines is that the best mindset to keep is probably just think of them as threads. Don't do with them anything you wouldn't do with threads. Like launching them like out of the blue in the middle of a process, it's possible because they're so cheap, but it won't necessarily lead you to nicer code. Like the code here will become much nicer once we try to think of the coroutines as just threads. Okay? So let me show you what that means. All right. So the prepare method is, it still kind of looks the same. We do initialize a channel, which is a new concept. A channel is kind of a queue for coroutines. It can only be used in coroutines. It's a coroutine primitive. It's a queue. In that case, we don't supply it any capacity number, so that makes it an unbuffered channel. Unbuffered means that once we insert an input into the channel, we are blocked until someone picks that input out of the channel. So basically, it's a queue of size 0, if that makes sense. In addition to creating the channel, we call a create work pool, which, as you can imagine, just creates our coroutine pool as if they were threads. We're going to see what that means in a second. But notice our execute method. The execute method had become a lot simpler. Like it does nothing right now. So basically, what we do here inside the coroutine is just send something into the channel. And as I mentioned, this is a channel of size 0. So the send call will suspend the coroutine, not real blocking, suspending. It will suspend the coroutine until someone picks up this input from the coroutine, from the channel. And I am running that inside a run blocking segment, which means that I am blocking the execute thread while nobody picks the input out of the channel. So in effect, what I'm doing here is producing back pressure because I'm blocking. And if someone picks the input quickly from the channel, I'm not blocking. So I am able to process more inputs as long as I'm under capacity. Now, how do I control the capacity? This is the create work pool method. It gets the worker number as a parameter. In this case, it's 50. I want to allow for 50 concurrent operations to run. And then I repeat this code 50 times. And for 50 times, I'm creating a new coroutine. Like I did before for each input, this time I'm only doing 50 of those. I'm creating this arbitrary number of coroutines. And as you can see, they all have infinite loops inside them, as if they were threads. Like very familiar if you've ever worked with threads. You're like, an infinite loop, sure. And we get the input off the queue. Again, very familiar if you've ever worked with threads, because that's what you do when you have threads. You got a pool, it all runs the same code, and you got a concurrent queue of some sort to get your inputs from. And that's how it looks like. And the rest of the logic in here is just exactly what we had previously in the execute method. So just this bit of code is exactly what you see here. And in that way, we are getting both of the things we wanted initially. We're getting back pressure, we're getting capacity limiting, we're getting simpler code. We no longer have an arbitrary 50 millisecond sleep of no reason. Actually, we don't sleep at all if we get a chance to. We don't have to sleep ever, like unless we're at capacity. And I think it's agreeable that this code is a lot nicer and easier to understand than the previous code. So that's basically what we have in production. We will publish, none of you are using Apache Storm, but we are gonna publish this code as part of a blog post that will handle this subject exactly. And we will publish this code for people to use. So if you want, you are more than welcome. This is not the actual production code. This is just a lecture version, but the production code will be published. And I'm not going to talk about exceptions. We don't have time for that. All right. So what's so good about that? What did we gain here? What's so wonderful? So what's really important for me to stress here is that besides just having your code work with coroutines and be more efficient, which is definitely something you want, and that's a win. Besides that, there's a hidden win here. There's a huge benefit that is easy to ignore. And I want to show a code example, the last code example. All right. So at the beginning, I showed you a basic bolt that does a key fetch from Couchbase. That's the exact bolt I showed in the beginning. So its API is super simple because it's blocking. You call Couchbase client.get, you get a document, and you use it. The code is sequential, super simple. When we wanted to transition that code to async code, it became super complex and bug prone. Like, this is not a trivial process. And if you're going to do that for 100 bolts, you're going to produce bugs because it's not easy. It's not trivial. Let's see how that looks like. Again, we're seeing how this implementation, very basic, looks like with the coroutine bolt that we just implemented. All right. So as you can see, it's extremely similar to the basic bolt example. The name of the function changed. We added suspend. The API call that we're making is now different, but the code stayed the same. So if I'm going to do this refactoring for 100 bolts or 1,000 bolts, it doesn't really matter how many, I'm not going to have many bugs because the code practically does not change. Its semantics doesn't change at all. No extra complexity. And that's a huge win because for us, Java was a choice because it's easy to modify. Java code is, you can modify it, you feel safe because of the compiler, you can do refactoring like in the IDE, you can change all the methods in the world with a single click. It's great for enterprise applications. Now, what Kotlin gives you with coroutines is exactly kind of this power to refactor your code, to turn code from synchronous code to asynchronous, a non-trivial process with ease. And that for us was a huge win. Now, I just want to show how that implementation, how to turn an async API, a regular async API like an HTTP client API, into a suspended API. So that's what's happening here. Like Couchbase itself, they don't provide a suspended API for us to use. So we got to piggyback off their async API and create our own suspended API. So what we do here is create an extension method in Kotlin, which means that basically this method would appear to be belong to the Couchbase client object, even though it's not. But we're creating this function, and we're initializing a suspend cancelable coroutine, which is just a coroutine primitive. Basically, it gives us a continuation object, and it says, okay, within the context, you do whatever async API you want to do, whatever async call. And in the callbacks, you just call back on the continuation object. And in that way, when Couchbase returns and calls back on us with an answer, we tell the runtime to resume the coroutine that it's been executing, to resume the previous stack. So in fact, we can turn any async API into suspended API very easily. We do that once per project, and then we can use the getSuspended method from everywhere and like seamlessly turn synchronous code into async code with almost no changes. And that was the big win for us. No worries about race conditions. Still more efficient since we're doing non-blocking I/O. Great wins.
Like in that situation, you're still holding the code, even if you change it to suspend, to async. Like, wait.
I'm sorry, what? In that situation?
Of course, like the calling thread is async, but the one that doing the sync call is holding the thread. Like you still need.
Well, you're talking about this example, or are we talking about the bolt itself? We're talking about this? So,
like you can't really transform an sync method to async method because the sync method still need to hold the thread.
Right. So this is not a sync method. This is I'm using the async API here. So this method it returns immediately.
I understand, but inside it's holding the thread for, like, it's waiting for I/O inside, no?
No. Since we're using the async API, the Couchbase async API.
You have async.
Yeah. Couchbase has async API. It just doesn't have suspended API.
You're using observable here. That's what's the reason for that? That's Rx in Java, right?
Right. It's just Couchbase forces you, like the async Couchbase API is using observable. They don't have any other async API.
There are a few things that it's not seamless. It's kind of stack-based. So there is some exception, and there is some, I don't know, some kind of debugging. They want to look on it, so I can't really step into like the synchronous thread local that unusual.
Right. Like
it's not it's not too much seamless.
I agree. It's in debug time. It's not seamless. Like you're gonna see, you can't step into suspended code. In stack traces, you're gonna see a difference. But in runtime, in the sense that how the code looks and behaves, you understand that you're not going to cause bugs. The code will be harder to handle because now it's async. It's inherently harder to handle, but few bugs.
What about logging? How do logs look? You basically have one thread that's running, behind,
So I'm transitioning from a point where I had one thread running my code, because Storm is like that, to a point that I still have one thread running my code. It's just a coroutine thread. So it doesn't really change for us. We didn't need to worry about how we do logging because it just worked the same.
Okay, but as far as filtering, or let's say you want to see a single process, then how do you filter for that?
Thread local, for the local.
Thread local.
I mean, if you are using multiple coroutines and you want that each coroutine will define some ID and you want to see in the logging a specific ID for specific code.
Oh, it's possible because first of all, you can define context on the, like I initialize a coroutine context at the beginning of each bolt. This context is it can hold data. You can use it to store stuff for you. Currently we name our threads differently. You can hold thread local state on this single state that thread that you created. So all these things are still possible, but all coroutines would share that same thread, and they will all share this context.
My question is, what do you differentiate between different coroutines in the logs?
In the logs, it's easy because for us it's easy because we have this match. One thread runs a single coroutine context, and this thread is named, so you can see exactly which thread. If you mean the exact coroutines, that's something. Like I said, many coroutines share this same thread. So currently we don't have this notion in the logs. We don't monitor the exact coroutines. Actually, we try to not log anything to disk. We just use Kibana for logging. But then we have the
start to end in the logs that looks.
Yeah, but then what we care about is the input. We have IDs that are relating to the input. We don't really care about the coroutine. The input is what's important. All right, thank you.